Hi, this video is on the Doppler effect, otherwise known as eow. You probably know the Doppler effect, not just from Sheldon Cooper on The Big Bang Theory, but also from everyday life. Let's say a police car is coming toward you, or a fire truck is coming toward you. As the vehicle comes toward you, the frequency gets smushed, as it were, which makes the wavelength shorter. And as the frequency gets smushed, it gets higher. The pitch goes higher, and so dun 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 dun. You're gonna hear a higher sound than you would actually hear if the fire truck or whatever was sitting still. And then as it passes you, the wavelength gets stretched out. The wavelength gets longer, which means that the frequency gets lower, which means that the sound goes down. So dun 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 dun. We all know this. Although my daughter still stubbornly refuses to believe that it exists, I think deep down she knows it does. But anyway, ladies and gentlemen, the Doppler effect. This video relates to Young and Freedman's University Physics, Chapter 16, Section 8. Well, let's dive right into it. So to start off with, let's say that we have a fixed source. We have a boom box. We have a radio sitting somewhere, and I'm listening, to it. And let's say I'm moving toward that fixed source of the sound. Well, a couple of assumptions. First of all, let's assume there's a straight line, that we're talking about a straight line between me and the music source. We could get into trig, we could get into ricochet sounds and radar, all that sort of thing. But let's assume that there's a straight line between me, the listener, and the source. And narcissistically, let's assume that the positive direction is from me toward the source. The positive direction is me toward the source. Okay, well, here's our first formula in this section. So the frequency of the listener, me, is going to equal the velocity of the sound plus the velocity of me, the listener, divided by the wavelength of the sound. Now, you may know by now the fundamental relationship that velocity flies. That is, v equals f lambda. Velocity equals frequency times wavelength. This makes sense because wavelength is a length, it's a distance, so like, say, meters. And then frequency is cycles per second. So if you take meters and you multiply it by per second, you get meters per second, which is a velocity. So it makes sense that velocity flies, or v equals f lambda. Okay, so let's say I'm moving toward the source. The source isn't moving, I'm moving toward it. We kind of know intuitively that the frequency is going to get smushed, and that the wavelength is going to get smaller. The pitch is going to go up because there is a moving towards the source of sound and me. And I mean, it would be the same if the source was coming toward me. But let's again assume that I'm moving toward a fixed source. And so the sense that there's going to be a plus here, and that therefore the frequency is going to up, makes sense. So the velocity of the sound, as if, which is standing there still, plus me, the velocity of me moving toward it, divided by the wavelength of the sound, is going to get me the frequency I hear, the frequency of the listener. Now this second part uses a little algebra. So let's say that you take lambda and you put it in terms of fs, the frequency of the source. So again, lambda is going to equal the velocity of the sound divided by the frequency of the source. So if I substitute v over fs for this lambda and do a little algebra, then I have a nice equation that tells me that the frequency that the listener hears is equal to 1 plus the ratio between the velocity of the listener and the velocity of the sound times the frequency of the source. So here we have a nice little equation for a simple situation where the source of the sound is fixed and I'm moving toward it. Okay, part 2. Let's say the source is moving and I'm moving as well. So what does this do to the wavelength? Well, the wavelength in front of the source is going to equal what it would have been naturally. So the velocity of the sound divided by the frequency of the source. That's kind of the natural wavelength. But because it's being smushed, the wavelength is going to get smaller. And therefore the frequency is going to go up. We kind of intuitively know that we're going to be taking the default wavelength and making it smaller because the thing is moving, right? And so we're going to subtract the velocity of the source by the frequency of the source from the original fixed, standing still velocity of the sound by the frequency of the source. And basically do a little algebra, and we have this little equation that tells me that the wavelength is going to go down in front of the source by the velocity of the sound minus the velocity of the source divided by the frequency of the source. Okay, by same token, we know that behind the source, let's say it's moving, you're going to have a stretching out of the sound behind the source if it's moving in that direction, which means that the wavelength is going to get bigger, and thus the plus. So we're going to take the resting wavelength, the velocity of the sound divided by the frequency of the source, and we're going to add the velocity of the source divided by the frequency of the source. Do a little algebra again, and we end up with this. Okay, so we can still go a little bit further. If we take this equation, which is basically the lambda that we hear behind, and we plug that into for this lambda here, we can come up with an equation for the frequency of the listener. And it ends up like this. That basically, if you have a moving source and a moving listener, and by the way, this turns out to be true whether it's moving towards you or away from you or whatever, this turns out to be a universal kind of equation for the situation. That the frequency that the listener hears is going to equal to the velocity of sound plus the velocity of the listener divided by the velocity of the sound plus the velocity of the source times the frequency of the source. This is the equation you want to learn for this section. Okay, this is basically we've gone through a bunch of kind of explanation of how to get there, but this is the gem. This is what it's all about. The frequency of the listener is going to equal this in relation to the frequency of the source. Then there you have it, the Doppler effect. Now, before they leave this section, they talk about electromagnetic wave shifts. Now here, the medium doesn't matter because at least as far as we know now, there is no medium, there's no ether in space. Electromagnetic waves don't require a medium. And so it's only the relative velocity of the source and the listener that matter. We don't have to worry about air or anything like that. So if the source is moving away, we call that a positive velocity. If the source is moving towards, we call that a negative velocity. Now this involves some relativity, but it comes out with this basic formula. That the frequency of the receiver is going to equal the square root of the speed of light minus the velocity of whatever the body is, divided by the speed of light plus the velocity of whatever the body is, times the frequency of the source. And so this is the formula that has to do with electromagnetic kinds of relationships. This is, by the way, how we find out about what's called the red shift. No matter where you look in the universe, everything is moving away, which implies that space itself is expanding. There's no center point. Everything is the center point, rather. Everything is expanding away from everything else. Space itself is expanding everywhere. And so no matter where you look in the galaxy, no matter where you point the radio telescope or the satellite, no matter where you look, everything is moving away, which means that the wavelengths are shifting toward longer wavelengths, and we call that the red shift, which was a key discovery in the development of cosmology in 20th century physics. Well, there you have it, the Doppler effect. We're gone.